Right. So what this lab is about, essentially, I will be introducing some new concepts to you. Okay. And the new concept that I want to introduce to you is called as stress concentration. And we will be learning by doing an example, essentially. Instead of me first talking about it, I'll go through an example and that will let you see what's going on. Okay. So we have a part like this where we have got a notch on these two sides. This part, the dimensions are specified over here, and it is being loaded along its long axis, right? So it's a typical kind of a component that you'll find in a machine. So just a simple example to demonstrate the principle. This is being fixed on one end. Okay, in this case, this is completely fixed, but you can have other fixtures as well. But to keep the results same for everybody, we'll use the same kind of fixture. So what we will be doing is, later on, you can see here certain groups indicated. So basically, I would like you to do this depending so each student can do this basically for any of these materials, but I will be demonstrating it for AISI 1020 steel, okay, and with a load of 26,650 newtons. So let's do this now. Essentially, we'll start by doing some hand calculations. So there are three sets of hand calculations. First is to calculate the gross and the net stress in the part, as well as the strain and the total change in length. Second is basically to find out stress concentration factor from a chart and then find out the maximum stress in the part. And third is to evaluate the margin of safety. So right now, what you already know, you can do part A quite easily based on all the things that you have learned so far in the course. Okay, part B and C are new concepts. No, part C is not really new concept, but we will be looking at in context of the new concept of stress concentration factor chart, which I will be introducing later in this session. So can I ask you to first of all do some hand calculations with this particular component, okay? So with this component, and basically tell me what is the net stress and what is the gross stress in this part, yeah? So should I give you 1 or 2 minutes? Will you be able to do it? So should I cast my screen on yours as well? Because I mean, for this it's not too important, but later on when we start doing the software, I think casting the screen will help you follow it more easily. Okay, so to find the net stress essentially and the basically the gross stress, so we are saying that this load is being applied over here and this is being fixed all along this face, right? This face is completely constrained, yeah? So if you are trying to find the gross stress, it has to be away from the notch. It can be in this region or it can be in this region, right? But then because of the notch, the area will reduce here and we expect the stresses to go higher. So I'm calling this as my region A, and I'm calling this from where it is passing through the notch as region B. So the gross area of region A is basically equal to the thickness, which is 12.71, times the height, which is 38.1. So it is 12.7 into 38.1 millimeters. Okay, so what is the area here? It is, can somebody do this on a calculator please? 483.87 millimeter squared. Now, to find out this stress, all you have to do is to take the force, which in my case was 26,650 newtons. Can you confirm that? Yes? So, we'll take this force and divide it with the gross area, which you have already worked out is 483.87. So the overall gross stress in region A, okay, is basically how much? Can somebody do that on the calculator? 55.1 megapascals. So that's the gross stress in our bar. In the region where the notch is, the area will be net area, and this will be basically the thickness is still the same, 12.7, but the height has reduced from 38.1. You need to take out one radius from this side, one radius from the top portion, right? From the bottom and the top. So it will be 2 into 6.75, which is the radius of the notch. 6.35, which is the radius of the notch. So what is the net area then? What's the net area? 322? 323 approximately? Okay, so what is then the stress in this case? The stress in this case will be sigma B, which is sigma net, and in this case that will be 26,650 divided by this 323.2. So how much that comes out to be? So sigma net is sigma B is going to be equal to 82.25, right? 45. Okay. I mean, it depends on your approximation, how much you have approximated the area, but it is something around 82.4. Okay? Yes.
So the net area, you said 12.7 times 38.1 minus the radius.
Yes.
But why did you subtract the radius? It's not even in the contact of 12.7.
So basically I'm talking about this area which is bearing the stress now, right? So if you think about it, this width is still the same, 12.7 is still the same, right? The depth, but the height has reduced.
Yes.
So the height has reduced. So to get this new height, you have to subtract basically from the original, which was 38.1, the notch radius from the top and notch radius from the bottom. So what I said was that this is the net area. So the area here is this one. The total height was 38.1. So you subtract the notch radius from the top and notch radius from the bottom to get the new height of this middle region.
So the A net is like that height? Small.
Yes, so now the height is this one over here. So this is now the new height, right, of the net area. Net height, H net. So that's H net is this, the original was 38.1, So H net becomes 38.1 minus 2 into 6.35. Okay?
Just decimal points is different in my calculator. I get 322.6 and then final.
Yeah, I know it. There is a bit of round off there, so that's why I said it is approximately this number. Okay, 82.1, maybe 82.4. So 82.6. Okay, doesn't matter, right? So let's move on. So this is something that you already know. There's nothing new here. I'm just repeating what we have been covering so far in this course. So the question is this value correct or not? Okay? The question is this value correct or not? While calculating this value, you are making some fundamental assumptions. And that fundamental assumption is about the stress state. What you are saying is that in your part, essentially, the stress field, which you can, let's say, represent by these arrows, right? When it comes to this region, the stress field in terms of the intensity increases, so the actual magnitude changes. Here it was 55, here it becomes 82, but you are not saying that this stress field has become non-uniform. You are still saying that the stress field itself is uniformly distributed, meaning these arrows are equally spaced, right? That's your fundamental assumption about this calculation. That's why you are able to use the entire area, right? And not that differential calculation, okay? What you will find in reality happens is something else, okay? So let me show you a picture, an image. Which will explain to you what's happening. So if you look into this image, what this image is showing you is that the stress field actually does not remain uniform. It was uniform over here in the gross area, but when it came near to this notch, right, the spacing between the lines has reduced. It's like you were going on a motorway and each car was traveling in its own lane, but suddenly the motorway became narrow. Now the same numbers of cars have to pass quickly through that, and what you will expect is that the traffic will no longer remain very uniform, right? So it's the same number of cars now passing through that narrow region, making it non-uniform, and there will be more cars crowded near this notch, and in the center maybe it will still be very similar to what it was before, like in the start. So the cars in the center may not move too much in the central lane, they can just keep on going straight, but cars on the side will try to converge, okay, because of roadworks, right? So if you think about it in this sense, it makes sense, right? But obviously in reality, material, you're not really having any flow of particles there in that sense. But think about it, a material is a continuum. Each particle, when you're going to stretch it, stretches on the other, and if there is a narrow region available, that displacement field, that strain field must become congested, it must become concentrated near that discontinuity, because you see, if it's a continuous material, you cannot have a jump from 55 to 82. You must have some progressive change, right? So there are two things. Firstly, there is progressive change, and that progressive change will necessitate that there will be certain regions where the distribution will become non-uniform. Because of that non-uniformity, the calculation that we did is okay as an approximation, but it's quite far from the true maximum value. And that's why we were taking a lot of safety factors previously. Okay? So let's try to have a calculation that will allow us to actually see what the true value of stresses are. Now there are several ways you can do this, right? One way to do this is to physically put some strain gauges on this thing, right? Physically mount some strain gauges and actually then measure the strain gauges just next to the notch and away from the notch. This can be done, but it's quite difficult and time consuming, of course, and you need specialized strain gauges that will have that small, area, so you're able to precisely measure it. Okay? Then there are other techniques these days. We have got like digital image correlation, where we use imaging techniques to convert the displacement field of each point to the strains and then to the stresses. Again, that is something that can be done, but you need specialized equipment and software for that. What we are going to do today is a theoretical calculation that we are not going to do by hand. Rather, we will use computer software. And this may be the first time that you are actually carrying this type of analysis. So this analysis which we will be going to do is called as finite element analysis. Okay? So it's called finite element analysis. Basically, in a nutshell, finite element analysis is a mathematical technique that discretizes the entire domain, which in our case will be this part case, yeah, into small number of elements. Not small number, small sized elements, but a large number of these elements. So think about it. Previously, you were just calculating the stress based on this average area. Next, you calculated it based on this average area. Instead of that, if I discretize the whole region into small squares or small triangles, I will be able to use each of these areas separately. But I will no longer be able to simply solve for this, because now I will have a large system of equations to solve, right? Because we have to make sure that the continuity of the system is observed through connection on these nodes where these will be joined, right? And then we will have different sets of equations written for each point. And then we will have to simultaneously solve all of those equations to finally get the solution. Okay? So that process can be done, but as the number of the elements become larger, it becomes quite difficult to do using hand calculations. That's where your softwares will come in. Okay? Now, you can write your own mathematical code to do that. Okay? But this is not a course on finite element methods. So I'm not going to teach you how to actually write your own code or do anything. Rather, I'm going to use a commercially available software package, which you are very familiar with, SolidWorks, right? But you have so far mainly used it for drawing and drafting purposes. So today we are going to use this for simulation or analysis purpose. Okay? So let's go there. But before we go there, let me also calculate another value through hand calculations that I said that we should calculate. And remember, I said we should calculate the total displacement, right? Total change in length of the part, okay? And also the strains. So the reason for doing all of these calculations is that I am trying to basically get some numbers that I can then compare with my computer analysis. Okay, so let's now quickly also calculate the total displacement, and after that I will go on to the simulation. So to calculate the total strain, right, basically the total displacement or deformation will be the sum of the displacement of region A and region B. Okay? I am now calling all of the region, both sides, as region A, right? If you're going to calculate it separately for one half and the other half, you can also do that, okay?
But we have to do
In that case, it will be 2 times delta A, okay? So basically, let me draw it to explain it to you. It's fixed from this side, right? And it's here, like this, okay? So I'm calling both of these sides total as A, and I'm calling this middle bit as my region B, okay? So this, so I will calculate delta B over here and delta A over here and here, right? So how we are going to do that? We can do that by simply taking the strain in region A and multiplying it with the length of, let's say I call this as A1 and A2. So length of A1 plus length of A2. So that will give us total for the region A, right? So into length of A1 plus length of A2, and then I can do epsilon B, which is the strain in region B, multiplied by the length of the region B. Now the length of A1 plus A2 will simply be, so this is going to be the total length minus the notch diameter, essentially. Yeah, so it is basically 2r that you need to subtract, okay? So if the notch has the radius r, then because this is a circular notch, so you will have 2r to be subtracted from here. So this will be basically L minus 2r. So that's the length that will go in this equation here. And length of B is simply going to be 2 times the radius, okay? Now, next thing is the strain in A that we need to know. So what is the strain in A? Is basically the stress in A divided by the material's Young modulus, okay? And the strain in B will simply be equal to the stress in B, and because it's the same material, so it will be the same Young modulus, okay? So let's now calculate these numbers. I have not given you in the problem sheet the value of the Young modulus, so that is something that you will need to look up from SolidWorks, okay? But instead of opening it up now and showing you, when I actually start doing the simulation, I'll tell you how to read the value from SolidWorks, okay? So, but for my case, for continuity, let me actually do this, let me tell you what the number is, okay? Because I already know what the number is, I have checked it up from SolidWorks. But you need to keep the same value as used in SolidWorks to make sure that you are able to compare the results, right? And it's not because of change of the Young modulus that you get any difference. So epsilon A is equal to, what was the stress in region A? 55.1, and the Young modulus of my steel is 200,000 megapascals, okay? So this is E from SolidWorks for which material? AI SI steel, and what was the number? 1020, okay? So this is the value that I have got from there. You can get it for your materials as well. Okay. So this strain comes out to be how much? 2.755 into 10 to power minus 4. Okay. In the same way, we can calculate the strain in the region B, which is the net strain. Okay. So the net strain will depend on the net stress. So strain in region B is going to be 82.4 divided by 200,000. This is 2 point, no sorry, not 2 point. How much is this? Anybody? 4.12. Is there any other after this?
No, that's
Okay. Into 10 to power minus 4. Okay. So now the delta total will be, so the total deflection will be the strain of A, which is 2.755 into 10 to the power minus 4 multiplied by length of the A region, right, which we already have calculated. And how much it was? The total length 165 minus the diameter 2r. So 2 into 6.35. So this was 165.1, I think, right? And this was 2 into 6.35 minus. So let me just confirm the dimension. Yes, 165.1 and then 6.35 was the notch radius. Right. This plus, now we will also add the second notch, the displacement in the middle zone. So this will become 4.12 into 10 to power minus 4 multiplied by 2r, which is 2 into 6.35. So obviously this will have a much smaller contribution because of this length is very small, and this will have a much bigger contribution because this length is much bigger, right? So the total displacement or deformation of the free end, yeah. Okay, so 47.44 into 10 to the power minus 3 millimeters, or you can write it. So now, so we have got some values to compare. We have got the total deflection, we have got the stresses, net stress, gross stress, that we will be now comparing with the computer simulation. So I'll just quickly stop the video over here, and then I will record again for the next part separately, so that you've got both parts separately.